side. There. Okay, finding general solutions. This is a little bit harder. And then once we learn how to do this, we'll find particular solutions, which is a little easier. And then we'll put it together. And then we'll actually find stuff that actually makes sense for why in the heck we use calculus to do this. Okay? Well, it makes sense to me. It might not make sense to you, but it makes sense to me why we use calculus for this. So hopefully for you, it'll make sense too. So when we find general solutions, we have to do what's called separation. I think that's how it's spelled. Of variables. Separation of variables. I'm no English person. I ain't got no English skills. Separation of variables. So you want all the y's on the left and all the x's on the right. Okay, how do we get the y's on the left? Well, we'll multiply by 3y squared. So it's 3y squared dy dx equals 2x. And then we're going to multiply both sides by dx to get the dx's on the right. So 3y squared dy equals 2x dx. That's easy, right? Then we're going to integrate both sides. So on this side, we're integrating with respect to y. On this side, we're integrating with respect to x. So if we do that, integrate is y cubed plus c basically, but we don't write the plus c here, equals x squared plus c. Because if we have a constant on the left side and a constant on the right side, we can just move the constants over and it's still a constant, because a constant minus a constant is a constant. 3 minus 1 is 2. 1200 minus 162 is whatever 1200 minus 162 is. They're still constants. So constant minus constant is a constant. Now, are we done? We would love to be, but we're not. We need to get y alone. How do we get y alone? Cube root of each side. So this is y equals the cube root of x squared plus c with c on the inside. And you will get to some cases where we need to take c onto the outside, but not yet. Let's just stop right there. Okay? Because the cube root of c is still c, but the cube root of x squared plus c, then that's where it makes it a little more tricky. So we're going to leave it like that. Okay. How does the separation of variables look like for this one? Well, our y's have to go on the left and our x's have to go to the right, right? So if we divide by y squared, it's 1 over y squared, correct? So it's y to the negative second, or 1 over y squared. Then we multiply by dx on each side. So I have 1 over y squared dy equals e to the x dx. Which one says 1 over y squared dy equals e to the x dx? B does. Because the dy does not go to the denominator like it says in C. It is B. That's our separation of variables. Marcus tried to solve this equation. This is his work. Got to do separation of variables. So what did he do? He multiplied both sides by 3y squared and 1 over x squared. Then he integrated it to make y cubed minus 1 over x plus c. Then he took the cube root of each side. Does that look right? Or did he make a mistake somewhere? Now, Zaria is saying he should have just moved the y squared without moving the 3. But no, the 3 we like to move over with that. In this case, only because that 3 becomes a cubed. And that's why we moved the 3. Would it have to move? No. In this case, it helps us by moving it, so that's why we move it. Will we move the coefficient every time? No. It just depends if it'll help us or not. So this looks correct. Okay? That looks correct. So, oh, it is incorrect. It is incorrect. No plus or minus. Jeez, I missed that. That's why we look at the answers. The right-hand side of the equation should be that, because it's a cube root, not an even power. If it's an even power, it's plus or minus. Cube root is just what it is. Okay. Look at this work here. First step, they multiplied each side by e to the y. Then if you integrate e to the y, you get e to the y. If you integrate 4 1 over x, it's 4 ln of x plus c. Then you have to take the natural log of each side to get rid of the e to get it down to y. So it's a natural log of that. Is his work correct? Because it sure looks like his separation of variables is done correctly, right? Yep. So we've got that. The right hand of each side of the equation, they said should be this. No, I don't think so. I think it should be within the ln, because the ln will affect that c, whatever that c is. So that needs to be in parentheses. So I would say Ty's work is correct. Solving this equation. Ooh, boy. Now, I'm going to do maybe an extra couple steps compared to what you might do, just to show you why I'm doing it. I'm going to take this and multiply the top and bottom by 2 before I ever start shifting the y over. Why? Because I want one instance of y on the left-hand side or right-hand side, not 2. So it's x squared over 10y minus 2x over 10y. And then, so dx, dy, dx, 4x, thank you. Dy dx equals x squared minus 4x all over 10y as one instance. So then what are we going to do to each side? We can multiply by 10y. That'll be fine. So 10y dy equals x squared minus 4x dx. Then we are going to integrate. So if we integrated, it's y squared, right? But I had a 10 out front, so really it's 5y squared to make 10y here. So I need to reduce that down to a 5. Equals 1/3 x cubed minus 2x squared plus c. Now what? Divide by 5, exactly. So y squared equals 1/15 x cubed minus 2/5 x squared plus c. Okay, because c, a constant divided by 5, is still some constant. Now take the square root. So we need a plus or minus x cubed over 15, 2x squared over 5, plus c, and I would keep the c inside the radical. Okay. All right. This one. So I'm going to say dy, and then to move the y, I'm going to go 1 over y. So 1 over y dy equals negative 10x to the 4th dx. Then what do? Integrate. So ln of y equals x to the 5th with a negative 2 in front to make negative 10 plus c. then we're going to do what to each side? E both sides. Okay, here's where it's really important that you pay attention. E to the ln of y is just y. You get that. This is e to the negative 2x to the fifth plus c. Or when you add exponents, that's what you do when you multiply the same base, right? Watch what happens. Negative 2x to the fifth e to the c. When you multiply bases to combine them into one base, you add the exponents. So if we're adding an exponent with a c in it, and with an e as a base, we will separate this as e to the 2x plus 5, e to the c. Important, 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 because this is how we're going to develop our next thing we go on to in a couple days. Okay? Then, what's e to any constant? Still a constant. So in the end, it'll become e to the constant, which is a constant, e to the negative 2x to the fifth. It'll be that, which is that. And then when we get population growth and population reductions and amoebas and all kinds of other stuff that we're going to talk about, that's what we use. Because this is logarithmic growth, and there's a lot of logarithmic growth and decay that use this equation. Yes, sir.
Why does e to the c cancel?
E to the c does not cancel. E to a number, is a constant. So e to the fifth power is some number. And so that number we just put out front. Yeah. I know seeing it the first time you go, what? But that's the way it works. Okay? So since this is just some random number, then we can rewrite it as just some random number. Because a constant is a constant. We don't know what number it is, but it is a number. So e to some strange number is still some number, and it comes out front. And actually, we'll be solving for that c when we get in the future problems. And then that constant will be our constant of proportion or our constant of variation, and thus lead us to the answers. So, super important that we learned this one there. Okay, let's look at this one. Woo-wee. This is a problem. What we have to do is start simplifying the right side before we can even think about separating variables. So, dy dx equals x squared y squared over 8 plus y squared. So, dy dx equals x squared y squared over 8 plus 8y squared over 8. So then we're making it one fraction. Dy dx equals x squared y squared plus 8y squared all over 8. Everybody picked up what I put down there, right? We just made it one fraction. Now, to get our variables separated, we have to do the dreaded factor. We had to factor out a y squared to get x squared plus 8. Now we've got separation of variables. So we go 1 over y squared dy, because we're dividing both sides by y squared to get rid of it, equals 1/8 x squared plus 8 dx. So 1 over y squared dy is negative 1 over y if we integrate. If I distribute through, I get 1/8 x squared plus 1. That's really this. So if I integrate 1/8 x squared plus 1, I get 3 1/8. Nope, I don't. I get 1/24 x cubed plus x, right? Because 3 times 1/24 is 1/8 x squared. Yeah. Plus c. Okay. Now what? Take the reciprocal of both sides. So negative y equals 1 over 24 x cubed plus x plus c. Multiply by a negative, y equals -1. And then we have to multiply both the top and bottom of this by 24 to get rid of the 1/24th, so we don't have a complex fraction. So it's -1 over x cubed plus 24x squared, or 24x, I mean. And then what's c times 24? C. And then, so 24 times -1 is -24. So it's -24 over x cubed plus 24x plus c, which is that one. Okay, what if we have a trig one? Yeah. If we have trig, 3y minus y squared equals cosine of x dx. Can we integrate it? Can we separate variables? Yep, we could separate variables. Because they asked if we can solve this using separation of variables. Yep, we can. It'd be really ugly, but yes, we can. Can we solve this one by separation of variables? So we have, if we add 3y to each side, we get 3y plus dy dx equals 2x plus 6. If we multiply by dx, no, we cannot. We cannot because of this plus sign. Kills us. So when it's addition, subtraction, that's a no. We cannot. We have addition here, but it's an e. So dy dx equals e to the x, e to the y. Are we out of time? Oh, no, you guys gotta, where are you guys going? I forget. Okay. Yeah, okay. And then we can separate the variables here because 1 over e to the y dy equals e to the x dx. So when it's plus on an e, when it's in the powers, yes, we can separate variables. Okay, so is it out there? No, it's not. No, it's not. So let me put it out there for you. And just think you have all kinds of extra time to work on calc today.